Hello everyone, welcome to my new video. In this video, we'll learn in detail about chapter 1 of your ninth standard, which is number systems. We'll start broadly with categorizing numbers into different categories, and we'll also see some tips and tricks surrounding on how to determine which category your number belongs to. And we'll then further proceed in solving some example problems from your NCERT textbook. All right, so exciting things ahead. Let's get started. Now, the universe of entire numbers or entire number system is broadly classified into two categories: real numbers and imaginary numbers. Before I go any further, I'll just clarify that imaginary numbers is something that you will study in your class 11th. Okay, so we won't worry a lot about imaginary numbers. Right now, we'll be just focusing on real numbers. But for anyone who is interested, I'll just mention that imaginary numbers are numbers which are square root of a negative number. Okay, so for example, if let's say it is square root of -1, square root of -2, square root of -10, and so on and so forth. These numbers are imaginary numbers. Okay, but as I discussed earlier, in this video, we'll be just focusing on real numbers. Now, real numbers get categorized into two broad categories: rational numbers and irrational numbers. Okay, real numbers can be just of two types. Either a real number is rational or a real number is irrational. I'll also highlight that real numbers are represented with capital R, imaginary numbers are represented with capital I. Okay, rational numbers are represented with capital Q. Okay, and irrational numbers are represented with Q dash. Okay, let me highlight those notations. So real numbers are R, rational numbers are Q, irrational numbers are Q dash, and imaginary numbers are I. Okay, we'll try to remember those notations or representations as well. All right. Now let's see what's the difference between really rational number and irrational number. Let's actually start with irrational number. Okay, let's study irrational number in detail. All right. Now let's look at how to determine if a number is irrational or not. Now, in order to determine if a number is irrational or not, there are really two conditions which I like to see. Okay, so there are two conditions, condition number 1 and condition number 2. If these two conditions are satisfied, the number is irrational number. Okay, condition number 1 is that the number is non-terminating. Non-terminating. Okay, so that's condition number 1, that the number is non-terminating. By non-terminating, it means that the number does not end, or the decimal portion of the number goes on forever. It does not end. Condition number 2, and there is and between those two conditions, and there is no repetitive pattern. No repetitive pattern. Okay, we'll look at these conditions with example, but if whenever a number meets these two conditions, condition 1 and condition 2, then such a number is irrational, or if not, it's a rational number. But if these two conditions are satisfied, then that number is an irrational number. Okay, let's look at an example. Let's say example, the number is 1.375298 and dot 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 dot. Now let's see if this number is rational or irrational by looking at these conditions. Now let's see if this condition number 1 is satisfied. Is the number non-terminating, or it does not end? Yes. If you see this dot dot dot, that means the number is non-terminating, or these decimals does not end. It goes on forever. Okay, so condition number 1 is satisfied. Now let's look at if condition 2 is satisfied. No repetitive pattern. Do you see any repetitive pattern here? The numbers are 3, 7, 5, 2, 9. There is no really any pattern that I can see here. They are just random numbers and it just goes on. There is no really pattern. So the condition number 2 is also satisfied, that there is no repetitive pattern. So since condition number 1 and condition 2 is satisfied, this is an irrational number. Okay, does that make sense? Let's look at another example. 1.373737 and so on and so forth. Now, can you say that the number is non-terminating or it does not end? Now, when you see this dot dot dot, that tells you that the number does not end or it's non-terminating. Okay. What about second? So the first condition is satisfied. What about the second condition? There shouldn't be any repetitive pattern. Is there a repetitive pattern here? So the answer is yes. If you see this 3 7 3 7 3 7, so that's a pattern that I see. So this condition number 2 is not satisfied in this case, because condition 2 says no repetitive pattern, but there is a repetitive pattern here. So the condition 2 is not satisfied. That tells me that this is a rational number. Okay, let's look at another example. Uh, let's say the number is 3.756756 and so on and so forth. Now let's look at condition 1. So the condition 1 is the the number is, or the decimal part of it is non-terminating. So if you see here, uh, this is non-terminating because it does not end here. So yes, condition number 1 is satisfied uh, because it should be non-terminating. It should keep on going forever, which is satisfied. Let's look at condition number 2. Condition number 2 says there shouldn't be any repetitive pattern, no repetitive pattern. But here if you see 756, 756, that's a pattern that gets repeated. 756, 756. So condition 2 does not get satisfied because there is a repetitive pattern. So this is a rational number. It's not a irrational number. It's a rational number. Okay, does that make sense? Let's look at few other examples. Let's look at the number root 2. So the number root 2 can be written as 1.41421 dot. Now let's look at two conditions. Condition number 1 is that it should be non-terminating. It should not end. So does not end. Okay, so this condition is getting satisfied. So condition number 1 is satisfied. Condition number 2, there shouldn't be any repeating pattern. If you see your condition number 2, no repetitive pattern. Now, I really don't see any pattern here that I can really make out. 4, 1, 4, 2, 1. So there is no pattern that I can see. So if there is no pattern, the condition 2 is also satisfied. If condition 1 and 2 both are satisfied, then it's a irrational number. Okay, I hope that makes sense. So whenever you want to determine whether a number is a irrational number, you just have to see these two conditions. Condition 1, that the number should be non-terminating. That means it should not end. There should be a dot 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 in the decimal portion. That means it should just keep on going forever. Condition 2 is there shouldn't be any repetitive pattern. Whenever you see a pattern like this, it's not a irrational number, but it is a rational number. Okay, I hope that difference is clear. If these two conditions are satisfied, then it's a irrational number. So I would just like to highlight one important note here. Not only square root of 2, which we found out is irrational, really square root of any non-perfect square, like square root of 3, square root of 5, square root of 6, and so on. If you try to calculate those, you will see that both conditions 1 and condition 2 will be satisfied, which makes them all square roots of non-perfect square as irrational. Okay, it's an important note actually to remember. So I would also like to write it down. So let me write it down actually in this note. So square root of a non-perfect square is always irrational. Okay, remember it has to be a square root of a non-perfect square. So for example, if it's square root of 4, 4 is a perfect square because square root of 4 is 2. So since it is square root of 4 is a perfect square and the number comes out to be 2, and 2 does not satisfy either condition 1 or condition 2 because 2 is just like 2.0 and it just ends here, right? So it's not even non-terminating. For the number to be irrational, it should be non-terminating, but it ends here, so it's terminating, so it's rational. So but remember, if a number is a square root of a non-perfect square like 3, 5, 6, 7, square root of 8, really, square root of 10, and so on, all those are irrational numbers. Can you tell me what is square root of 25? So if it is square root of 25, that is 5. And 5 is just like 5.0. So it's ending here. It ends. It is not non-terminating. It is terminating because it's just ending here. So this is rational. It is rational because this is a perfect square. Okay. So it's only the square root of a non-perfect square. So square root of a non-perfect square. I'll just highlight that. Square root of a non-perfect square is always irrational. Otherwise, it's rational. Okay, so that's a very important note to keep in mind. One thing I want to mention that all these notes will be accessible to you via a PDF link, which I'll share in the description. Okay, so do not worry about losing those notes or writing everything down. You can write it down if you really like, but all these notes I'll make it available via PDF. Okay. All right, now let's try to understand rational numbers in detail. All right, now rational numbers are further categorized into two parts or two categories, which is integers and non-integers. Okay, now integers are represented with z and non-integers are represented with z dash. Remember, the rational numbers are represented with q. I'll like to highlight those notations. So rational numbers are represented with q, which are further classified into integers and non-integers. Integers are represented with z, non-integers are represented with z dash. Now, integers, it's very simple to identify. Integers are something without a decimal, so no decimal, right? So since if whenever there is a no decimal point, it's an integer. So numbers, so let's say if this is a number line, right? 0, 1, 2, 3, and so on. Then there is -1, -2, -3, and so on. So all those numbers 1, 2, 3, 0, -1, -2, -3, these are all integers. So uh, these are all integers because they don't have a decimal point in it. Okay, so these are all integers. All right, does that make sense? All right, good. So remember that integers are the numbers with no decimal points, which are basically the numbers on your numbered line that you can see: -1, -2, -3, 0, 1, 2, 3, and so on. All right. Now integers are further classified. Let me just
write this down like this. So integers are further classified into two categories, or really three categories: positive integers, negative integers, and zero, just the number zero, which is neither positive nor negative. Okay. All right. So positive integers are numbers 1, 2, 3, and so on. Negative integers are -1, -2, -3, and so on. And number 0 is just the number 0. Okay. I hope it makes sense so far. So integers can be further categorized into three categories: positive integers, negative integers, and 0. Okay. Now positive integers, the numbers from 1, 2, 3, 4, 5, and so on, are also called as natural numbers. Okay. 1, 2, 3, 4, 5, and so on are also called natural numbers. And if you combine the natural numbers and the number 0, there is another category that comes up, which is whole numbers. Okay. I hope it makes sense so far. So whole numbers would be 0, 1, 2, 3, and so on. Your natural numbers would be 1, 2, 3, 4, and so on. So all those are natural numbers. If you add a number 0 here, then that set is a whole number. Okay, I hope it makes sense so far.
All right, now let's see how to identify if it's a rational number or not. Now, in order to identify if a number is a rational number or not, it's now important that we kind of define what is a rational number, or mathematically how rational numbers are defined. Now, mathematically, a rational number is defined as any number which can be written in the form of p divided by q, where p is integer and q is also integer. So any number, numerator over denominator, any number which can be written in the form of p divided by q, where p and q both belongs to integer z. Okay, this symbol is called belongs to. Let me highlight that. So this symbol here is called belongs to. The symbol is called belongs to. So our P as well as Q belongs to Z, which is integer. Now remember, integers are anything without a decimal, okay? Rational numbers were categorized into two parts, integers and non-integers. Integers are represented with Z, and integers are anything without a decimal, okay? So keeping that in mind, remember that any number which can be expressed in the form of integer over integer is also rational. It can get kind of trickier. So integer is also rational. Integer over integer is also rational. Okay. And also other thing is q is not equal to 0 here. Okay, because if my q becomes 0, my number is not defined. So I don't want my number to be not defined. So I make sure that I put my q as not equal to 0. Okay, so any number which can be expressed in the form of p over q, which is integer over integer, is a rational number. Now let's take an example of number, let's say 5. If I see number 5 can be written as 5 over 1, which means it can be written as p over q, where p is my integer, q is my integer. Hence, my number 5 is a rational number by definition. Now let's look at another example. Let's look at number 2.3. So number 2.3 can be written as 23 divided by 10, where 23 is p integer, 10 is q, which is integer. So I could write that 2.3 as integer divided by integer, which makes my number 2.3 also as rational. Now it's in order to distinguish this, generally it's best to first kind of see if the conditions of irrational numbers are satisfied. Now, if I remind you, the conditions of irrational numbers, any number which is non-terminating, that means it does not end, which is kind of recurring or non-terminating. And if there is no pattern at all, such numbers are irrational numbers, right? We learned this few minutes back that any number which is non-terminating and which doesn't have any repetitive pattern is a irrational number. Now remember that while doing rational number, any number which is not irrational number automatically is a rational number. That was the reason actually that we did irrational numbers first. So if you know that if it's not an irrational number, it is for sure a rational number. And if it's a rational number, you can write it as in the form of P over Q. Okay. Let's look at another example. 2.3725. Is this a irrational number? Let's see. Is this non-terminating? No, it terminates. There is no dot 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 in the end. So it is not an irrational number for sure. Just on that basis, we can call it rational. And since it is rational, there have to be a way I can write it in the form of P over Q. So in this case, it will be 23725 over 1000, or I should say 10,000. Okay. So this is my integer over integer. So any number which is not irrational automatically is a rational number, and every rational number can be written in the form of P over Q. I hope that makes sense. Now let us look at few examples to kind of better understand how to identify or differentiate between rational numbers and irrational numbers. Okay, let's look at example 1. So we have the number 2.757575. Now, can we say, is this non-terminating? So that's the first thing generally that I like to see. So yes, it is a non-terminating. That means it does not end. So it does not end here. Okay, so if it does not end, there is a chance that it could be irrational, but there is another condition that we see. Let me give you a reminder. Again, so there are two conditions that we like to see for irrational. It should be non-terminating. It should not end. The decimal should not end here, and there should be no pattern at all. Okay. So let's see if the second condition is satisfied. The first condition is satisfied that it does not end. What about the second condition? So the second condition, there is 7, 5, there is 7, 5, 7, 5. So there is a repetitive pattern of 7, 5, 7, 5, 7, 5. So since there is a pattern, this is not a irrational number for sure, since it doesn't satisfy the both conditions for irrational number. Just on basis of that, this becomes a rational number. Now, someone might question, if it's a rational number, how can you write it in the form of P over Q? Because if it's a rational number, there should be a way that I can write it in the form of P over Q. Now, that's a very interesting question to have. We'll be looking at a similar problem in the next video. So keep following, and we'll try to convert a decimal or a number like this, which does not end but is a rational number, in the form of P over Q in the next video. Okay, but for now, remember that this is a rational number and it can be converted in the form of P over Q, which we'll do it in the next video. Now let's look at next example, which is root 3. Now root 3, we already understood that square root of a non-perfect square is a irrational number always. So if you look at this example here, where we have a note, square root of a non-perfect square is always irrational. We saw the example of root 2, 1.41421 dot dot dot. it does not end, and there is no pattern, which makes it irrational number. Similarly, square roots of all the non-perfect square are always irrational. So which means root 3. So the value of root 3 is actually 1.73205 dot 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 if you try to calculate it. So it is non-terminating and there is no pattern that I see, and which makes it irrational. Okay. Now this is an interesting one. 22 over 7. Now 22 over 7 is like P over Q, where my P is integer, and Q is integer. So if I can write it in the form of P over Q or integer over integer, that makes it rational. Okay. Now someone might question that, wait, pi earlier you said is irrational, but 22 upon 7 you are saying is rational. But how come if pi is equal to 22 upon 7, how come 22 upon 7 be rational? Now, the value of pi is actually the exact value is 3.142 dot dot dot. So 22 upon 7 is just the approximate value of phi. Pi in itself is an irrational number. Okay, because there is a non-terminating decimal and there is no specific pattern that I see. Okay, so pi is irrational number. Its approximate form is 22 upon 7. It's not an exact form. So pi is not equal to 22 upon 7. It's a very important thing to keep in mind, okay? Yes, pi is just approximately equal to 22 by 7. It's not exactly equal to 22 by 7. So even though pi is irrational, 22 upon 7 is a rational number, okay? I hope that difference is clear. Now let's look at this number, 7.8765983. So since there is no dot dot dot. So there is no, so this is a terminating decimal because there is no dot dot dot. There is no non-terminating end. Okay. So since it terminates, it's a rational number. And if it's a rational number, it can be written in the form of P over Q. So this becomes a rational number because there is no non-terminating decimal here because the decimal ends at this digit. There is no dot 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 after this point. So that just that makes it rational number, and since it's a rational number, it can be written in the form of P over Q, which I can easily write 7.8765983 divide by 1. How many zeros? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I just shift the 7 decimals. So 1, 2, 3, 4, 5, 6, and 7 decimals. So I just I just add 7 zeros in the denominator. Okay, so that makes it rational because this is integer and denominator is also integer. So that makes it rational. Okay, all right, now let's look at E. Now, E in mathematics is a irrational number by definition. Actually, the value of E, the exact value of E, is 2.71828 dot 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 dot. So it's a non-terminating, and which means it does not end, and there is no specific pattern that I see of here for the digits. So that makes it a irrational number. Now, E is an important number to keep in mind as it comes in your higher classes, in the chapters like logarithm, differentiation, integration, and many other math subjects related to mathematics in your higher studies as well. So it's important thing to keep in mind that E although they are not going to ask you in your ninth class most likely, but it's important thing to keep in mind that it's a irrational number. Okay. All right. Thank you so much for watching the video till the end. All the notes that we have done here will be available to you in the description, will be made accessible to you, so you don't have to worry about losing any notes. Also, if you have any questions, feel free to put it in the comment box. I'll try my best to answer them as soon as possible. Okay. All right. Thank you. Thank you so much for watching. Keep following. Thank you.